Hello all, I'm not dead. Okay, so hyperthreading. If you wanted to learn more about hyperthreading, then you came to the right video, because what this video attempts to achieve is to give you a working knowledge of the concept or technology of hyperthreading or other SMT technologies. This is important so that you can make better decisions, as you will now be educated on what SMT is, so you can use this to better your decisions as a programmer, a user, or somebody looking to buy hardware, whatever it might be. So hyperthreading. First thing that we want to understand with hyperthreading is that it is Intel's implementation of a technology called SMT. It is important to understand that Intel did not originate this concept or technology. It is simply their implementation of it. SMT exists out of the context of Intel. So what SMT is, as it's obviously an acronym, is it is simultaneous multi-threading. Okay, that's what the acronym stands for. And what SMT is it is a core's or a processor's ability to run multiple threads at the same time. Okay. Now, in order to understand what SMT is, it is important to understand what the concept of a thread is. So let's make a few instructions. Okay, let's just make a little mini kind of program here. A list of instructions that all depend on each other. Okay. So in our first instructions, we're gonna have a variable called a, and then we're gonna set it to 2. And then in our second instruction, we're gonna increment it by 1. And then in our third instruction, we're gonna make a new variable called b, and it is going to be equal to a plus 5. These instructions are completely arbitrary. The point that we're trying to illustrate here is that we have 3 instructions, 1, 2, 3, and they are all dependent on each other in their context and their sequence. Okay, so sequence is important. Whoops, that's pretty ugly. Sequence and context. Okay, so firstly, sequence. It is important in this program that instruction 1 runs before instruction 3. This is important because in both instruction 2 and 3, we are referencing a variable called a, and this variable does not exist unless we create it in 1. So if we try to run instruction 2 or instruction 3 before 1, these will fail because a does not even exist. So this illustrates that the sequence that the instructions are run in is important. It must go 1, then 2, then 3. It may not go in any other order. The sequence is important to preserve. The next thing that is important to understand is the context is important to preserve as well. Let's say we have 3 different programs here, okay? And they all have a variable called a. In this first thread, in this first program, if it says set a or increment a by 1, for example, in the second instruction, it is important that it affects this program's a, not this program's a. Even though these variables might be called the same thing, it is important that the context is preserved. So that is what a thread for our purposes of understanding multi-threading is. It is a sequence of instructions all within the same context. Okay, so now that we understand what a thread is, let's take that thread and let's create 2 of them. These are both identical right now, but that doesn't matter. Let's call one thread A and one thread B. Okay, and now let's make a little block diagram of a CPU. Okay, so we're gonna have our 4 machine cycle steps. Okay, let me just do a little bit of work here first. We're going to have our fetch, our decode, our execute. We have 2 execution units in this case and 2 storage units in this case. This is the machine cycle, and because we have a duplication of the resources of the core, we have a superscalar architecture. If you don't understand what superscalar is or what the machine cycle is, I have a couple other videos that explain that. They're like 5 years old, but you could also Google the concepts, look for another video on YouTube, whatever. Anyways, we have our block diagram for our CPU here, and now let's take thread A and run it through. So what happens when we put thread A is the instructions go in, one goes in, and then you move on to the next stage. One is over here, or sorry, you move on to the next clock cycle. One is over here, two is over here. You move on to the next clock cycle. One is being executed, two is being decoded, three is being fetched. We all understand that the thread goes through the pipeline of the machine cycle and it runs through the core. Now, what is important to understand here is that a core can only run one thread at a time. So let's say you have, 5 different programs running on your computer at a time. Let's say you have, Chrome, Discord, whatever. You have 5 different programs, and let's say, for argument, that they all take one thread each. Let's also assume that you have a 1-core CPU. Okay. Now, if you have a 1-core CPU with no SMT, you cannot run those 5 programs at once. You can have the illusion of those 5 programs running at once, but they do not actually run at once. What happens is the CPU continuously switches between each of these 5 programs. It will do a little bit of processing on 1, and then it'll switch, do a little bit of 2, 3, then 4, then 5. And each of these times that it switches, it does something called a context switch. And this is an important concept to understand as well. Okay? A context switch is something that is very resource intensive, because when you are switching, you have to do something called a pipeline flush. You have to do a few other things, but the main resource wastage here is you have to do something called a pipeline flush. Okay? So now let's just go back to our 2 threads here, our thread A and thread B, and let's say you've been running thread A and you've been doing it for 10 seconds. Okay, so the CPU, this whole CPU, is fully saturated by the instructions of A. You have instructions of A throughout the whole thing. You have it in the fetch, you have it in the decode, you have it in the execute. It's everywhere. Okay, it's in here. It's like a virus. Okay, and then you want to switch to. I'll put those back. And then let's say you double click this program, you double click onto thread B, and you want to run thread B's program. Intuitively, you would think, okay. You have your fetch, your decode, your execute, your store units. Well, if we run these 2 programs, A and B, then we can just throw both of them in there, and we can just intermingle them, no problem. This is whatever. We can just have A and B on the same processor, and they'll just run. This is not the case. What actually has to happen is A has to be completely flushed out. Okay. So when you double click, when you have your CPU fully saturated with the instructions of A, and then you double click onto thread B, in order for thread B to be processed, you have to do something called the pipeline flush, and the way that happens is the scheduler sets in a mechanism where it stops accepting the instructions of A. And then it lets all of A's instructions expire and go through the pipeline and not allow any new ones through. So on the first clock cycle that you just clicked B, you have your CPU and it is fully saturated with the instructions of A, and it is now blocking off any additional instructions from coming through. The next clock cycle goes, nothing is in the fetch. A is still in all of this. The third goes through, nothing is in fetch. Nothing is in decode. These 2 are still saturated. And then you have your fourth, nothing is in execute. Obviously, there's still being something here. And then in the 5th clock cycle, you have a completely empty pipeline. Now that you have a completely empty pipeline, you are now allowed to run thread B. As you can understand, this is obviously very resource wasteful. It is wasting a lot of execution and a lot of data power, because every time you make a context switch, you have to effectively completely wipe the state of the CPU's pipeline. You have to empty it out to allow the new threads, information, and data and instructions to flow in. Now, you might have a good question at this point of why. Why can a core only run one thread at a time? There are a lot of reasons for this, but let me give you one example that is very easy to illustrate. Okay, let's say you have two threads within one context. Okay, let's say you have a single program and it has two different threads that the programmer has said that there's going to be two threads, two sets of instructions within the same context. Okay, their sequence does not have to be preserved. Their sequence not preserved. Okay, so these are not the same thread, as they might be within the same context, but the sequence is not tied. Okay. Now, let's say we have these two threads, and let's illustrate them now. Let's say there's thread A and thread B. And thread A is very simple. It just says, okay, while A equals 0, run func x. Just run this function. And then B's thread is going to say every 1 second increment A by 1. Okay, so now let's say for whatever reason, let's say you have our CPU, and we're going to run both of these in at the same time, and there's no SMT, and we're not going to switch the context, no context switching. And let's just run these two threads into the CPU. Now you have to understand that the innards of a CPU is a bit of a jungle. It's a dangerous, unpredictable environment where anything can go. Literally, like, while these are very logical devices, their inner workings, because there's so much involved, things do not behave predictably in here. So it is very important that there are a lot of safeguards and mechanisms in place to make sure that everything runs in the proper order. But let's say for whatever reason you're running these two threads at the same time on the same core, and let's say for whatever reason B does not run. Let's just say, for whatever reason it can't get access to the system's clock. Something happens. It cannot perform. Now you're going to have A perform its function continuously, while A should not be 0. It's going to continuously think that A is 0 because there's nothing that's going to change A from being 0, because for whatever reason B is not running. This could be for a number of reasons. I really cannot understate that the innards of a CPU are so unpredictable that there needs to be so many safeguards to account for everything, that if you have two threads running on the same core with no SMT and no context switching, you're going to have a situation where you could have B just be screwed, not run, and now A is going to continuously run even though it shouldn't. Even though it's very obvious that 1 second is going to go by, 2 seconds is going to go by, 3 seconds is going to go by, this thread is going to continuously run when it shouldn't. This is why a CPU core can only have one thread at a time, because there is a very real possibility of one thread continuously running with no problems, but another thread having an issue, and one of the threads is going to continue without even knowing that the other thread is having an issue, and they're going to have conflict. Now, what SMT allows you to do is SMT is a scheduler technology. It is largely a technology that concerns the scheduler in an architecture to smartly schedule instructions between threads that may or may not share a context to make sure that their sequence runs in a proper order. Okay, so let's picture that you have a scheduler here in this massive block diagram, where you have lots of instructions here from two different threads, and they're just chilling out, doing their thing. Without a SMT capable scheduler, these instructions will just run willy-nilly whenever they're ready. If this instruction has its data available and the instruction and the resource, the execution resource is available, it's just going to run through. It's not going to care if this should run first. It's not going to care if this should run first. It is going to care if this runs first or this one because it's within the same thread, but it's not going to be aware of these. In a scheduler where SMT is enabled, or not really enabled, where it exists, the scheduler will make decisions to see, okay, this now has everything ready. Should I run this first or should I run this first? It's going to act appropriately depending on how the instructions came in and what the context is to decide what to do. Okay, now that we understand that a CPU or a processor with SMT allows us to run multiple threads on the same core while having the safeguards and mechanisms in place to preserve the context, the data, and the sequence of all the different instructions on the different threads on the core, what does this allow us to do? Where does the benefit come in? Okay, so let's examine this. Okay, so let's say we have thread A and thread B again, and let's make our CPU architecture, our little block diagram. Okay, give me a moment. And we have our fetch, we have our decode, we have our scheduler. This is important as this technology mainly has to do with the scheduler. And let's say we have two different execution units. Okay, we have our store units. This is an ALU, which is an arithmetic logic unit. Mainly deals with like most typical mathematical instructions, and this is a SIMD execution unit, which stands for single instruction multiple data. This is for handling a lot of data at once and doing the same kind of instructions on them. Kind of, you know, the acronym kind of speaks for itself. Okay, now let's say we have thread A, and it is primarily concerned with doing whole integer arithmetic. Okay, the primary type of instructions on this thread is whole integer arithmetic. Okay, now let's say, thread B, oh, that's a little thick. Now let's say thread B also does that. Okay, so now let's say we have, we add our thread A and our thread B and we throw them in at the same time. We are going to realize some performance gains as we now no longer need to do any context switching, assuming that these are the only two threads that we have to run on our CPU. We no longer have to do context switching, which is great. We save some resources, we save some time, but we are not going to fully realize the benefits of this SMT technology because both of these threads do the same thing. They are both going to be concerned with this execution unit. They're going to contest over the same resources. Neither of these threads use SIMD. Okay, so you can have these threads run through the architecture all willy-nilly, and they are going to continuously contest over the same execution unit, and the execution unit can only run one instruction at a time. So theoretically, you could have, a whopping whatever, let's throw like 5 threads on this thing. You could throw as many threads as you want. At the end of the day, there's one ALU. If all of these threads want the same resource, the entire CPU will only go as fast as this one resource is going to allow it. That's an important concept to understand. Now, let's change that up a little bit. Okay. Now, let's say B primarily has to do with SIMD instructions. Now we have a fantastic scenario for SMT because now you're going to have A and B go through the architecture, and now they're not going to contest the same resources. They're going to be able to work together on different parts of the CPU and fully utilize the resources of the CPU. This is where SMT is fantastic, because without SMT, you would only be able to have one of these threads at a time. If you're only allowed to have A go through the CPU, then the ALU would be the only execution unit being used, and B wouldn't be allowed on because you can't have multiple threads on the same core without SMT. We've already explained why that is. And let's say the opposite scenario were true. Let's say only B were on the core, where only B were here. Now, again, the ALU is now lonely and completely unused, as the SIMD execution unit is the only unit being used in the execution stage. But with SMT, we're going to realize the largest performance gains, as now both are in use. And if we have storage units that pertain to different types of data that these two different instructions use, we are going to be able to fully utilize our storage infrastructure. SMT, given the proper workload, will be able to fully utilize a CPU's infrastructure to the greatest ability. And this is where SMT works best. Okay, so you now have a working knowledge of what SMT is. It is a technology that allows a CPU to have a scheduler that is capable of making intelligent decisions to run multiple threads on the same core without having them antagonize each other. It is a scheduler that is intelligent enough to have mechanisms and safeguards in place to preserve the sequence, context, and data of two threads to make sure that the instructions are run without them colliding with each other. It allows you to avoid context switches, which are very costly. It allows you to avoid them. It allows you to fully utilize a CPU's execution units. It allows you to fully utilize a CPU's storage units and other resources, so long as the use case allows it, of course. Now that you have a good working knowledge of what SMT is, let's go and dispel one of the most common misconceptions about it. And it is that SMT somehow adds cores. The crux of this problem is kind of over here, right here. Here's your device manager in Windows. The operating system, for all intents and purposes, does not see your CPU as a core, as like a collection of cores. It sees it as a collection of units that can run threads. I have a Ryzen 7 4800H. This is an 8-core CPU that can run 16 threads. If you count all of these up, you're going to get 16 units here on Device Manager, even despite the fact that there's only 8 cores. Sorry for that, I was trying to hold in a burp. As far as the operating system is concerned, it can run 16 threads. So in a way, it's 16 cores. But what is important to understand is that it is not 16 cores, okay? You might have heard the term logical cores thrown around or something like that. That's not helpful. That is not a helpful term. It is important to understand that a core is a physical thing. This is like something you can touch, something you can see, sort of. You can't really see it because it's really small, and silicone is usually silver in color, so you can't like actually see it. But it is a physical thing. A core is a collection of resources. Having SMT does not in any way duplicate resources, okay? Having SMT results in the same amount of resources. It just allows you to better utilize those resources by allowing multiple threads to run on your core. Okay? And that's pretty much it. You now have a pretty decent working knowledge of what SMT is. So, congrats. Yay.